that's going to be the fun part today is graphing some of these. Our goal would be to graph, before we leave today, be able to graph without a calculator two things called, one thing called rose curves and the other called limacons. And you'll know what those are and you'll know how to graph them before you leave today, hopefully. And there are some more graphs that we'll continue this exact section on Monday and show you some more graphs of other things too. Landscapes and spirals we'll do. And lines too, right? So in polar coordinates. And there are lots of other things one could graph in polar coordinates, but we're just giving you like kind of a sampling of things one can do in polar coordinates. All right, so I'm gonna, without any instructions, on the next page I have like some rules about rose curves, like how to approach them. But I think that really the best way to approach a polar graph is the way we're about to do it right now, and that is just cold. Here we go. Let's graph this without a calculator. R equals 4 cosine of 2 theta. Okay? We'll just do it the way you did on day 1. Just plug in some points and see what happens, and see if we can kind of get a feel for the qualitative nature of this graph. If you plug in 0 for theta, what do you get? 4. In fact, one might stop and ask a big picture questions like, what is the largest and smallest value of r here? That is, what values can this expression take on, 4 cosine of 2 theta, if you let theta be anything? 4 is clearly, and so the value we just got is in fact the largest this will ever be. That means that this will never, well, I shouldn't say that. What's the smallest value? Negative 4. Okay, so that means that this will never, this graph will all be contained within the circle of radius 4, center of the pole. So it all will live in here. That's cool to know. Is r ever 0? Will there ever be a time when 4 cosine 2 theta goes from negative 4 to positive 4? So do you think there's ever a time it's 0? It's a nice continuous function. So there is a time, and you can even say when it is if you like, but I don't even need to know. I just know that there will be a time when it's going to be here. Okay. What about at pi over 2, when theta is pi over 2? Plug pi over 2 in.
It's the same.
You get negative 4, so where are we? So in the pi over 2 direction, negative 4 units though. So we're actually here, right? So if theta is pi over 2, we're here. What about when theta is pi? When theta is pi, what do we get? 4 cosine of 2 pi. Yeah, it'll be 4 again, actually. So in the pi direction, we're going positive 4 units. And then what about in the 3 pi over 2 direction? You might predict. Yeah, even without plugging in, you might take a guess that we're here, but plug it in, actually. Yeah, you get 4 cosine of 3 pi then. 2's cancel out. So, all right, so this is the feel for it, and it does go through the pole at pi over 4 and some other values, right? All the over 4s and stuff. So you can just trust me that this is, did you see the order in which we plotted? As we swept this way, we hit that point, this point, this point, this point, this point, this point, this point, and then this point, right? So here it goes. You ready? This is the fun part. What do you think? There it is. It's called a rose curve with 4 petals, okay? And if you don't believe me that that's the picture and that's the order in which it's graphed, then let's do it here. 4. What's that? No one will know what order you actually drafted in when you do it on your paper. but you know, we're trying to be honest with ourselves. That is in fact the order it was constructed. So you don't have to draw it that way. You can just like draw like petal, 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 petal. But like if you really want to do it the way your calculator is going to do it here in a second, then you do it the way I just did, right? Do it in that order. Boom, 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 boom. Right? It's fun. Here, let's watch it with the little ball thing too. The ball is fun. I might ask a follow-up question too. How would you just get one petal? How about this petal right here, the one that's pointed in the 0 radian direction? Can you give me limits for theta min and theta max that would not produce the whole picture? It would only produce that one petal. What do you think it would be? I need values of theta that produce 0 and 0 for r. on either side of this petal, right? Yeah, let's try it. Like, right? I mean, we could actually do the algebra off to the side, but I think we have a guess maybe that it's negative and positive pi over 4. Let's see if we get that petal. Sweet, right? Okay. So we can play around with this, right? Let's see the whole thing again. You want to get, you could do 0 to 4 pi. You could do 0 to 17 pi. And you'd see if you go around a whole bunch of times. You could do, right? You just keep going forever. It could be fun. Anyway, whatever. Good. So I want you to understand. Isn't that fun? So hypnotic. Okay. All right. The general idea of how to graph these before I show you these rules. Okay. So here's the rules. I think I might even have pulled this directly from your book, right? So neat, right? But that's how I would approach it, the way we just did. I wouldn't memorize these rules. All right, it's certainly true, and I think it should make intuitive sense that A is the length of the petals we get. Cosine or sine doesn't matter. We'll still get a rose curve. It'll look a little different. We'll see in a second. We'll do another one. And now this is the part that's a little weird. We haven't said yet, right? Did you see what we got? If n is 2, which is the case we just got, right? Did you see that we got 4 petals? If n was 2, it was 2 theta inside. So we got 4 petals. So you might, I didn't give you a space and time here to create conjectures, but you might make conjectures. If n was 3, or if n was 4 or 5, what would happen? That's the question. You can play around with that in a calculator. So it turns out, though, that if n is odd, then we get n petals. So in a second, and actually I'm going to change this example here. In a second, we're going to do 3 sine of 3 theta. That's the one we're going to do. Okay. So how many petals does that have? It ends up it will only be 3, and that's a little bit of a mystery to us right now. We'll discover maybe why that's true in a minute. But right now it's kind of like that's interesting. Okay. And of course the petals on this one will be of length 3 also. Okay. So 3 sine 3 theta. Are you okay with my little correction? I just thought we just did a cosine one. Let's do a sine one just for fun. Okay. So my first question again would be the maximum value of this and minimum values are 3 and negative 3. So my question would be, when does that happen? When do we get r equal to 3 on this graph? It's a little, don't just do it intuitively. Maybe you just actually ask that question mathematically, right? That is to say, when is this equation satisfied, right? In fact, actually, we could say plus or minus, I guess, huh? Right? When is that equation satisfied? We can actually solve it and find the answer, right? When is sine at a max or a min? At pi over 2, right? And then pi units afterwards is when it will be a minimum and then a maximum again. So we could say pi over 2 plus some other stuff, right? Other ones as well. All I really want is that very first one. Right? Really. Right now all I want is 1 petal. Can I just even find out where 1 petal is? That's my first goal. Get 1 petal on the picture. So plus some other things, right? Plus pi n, if you like. And then divide by 3, you get what? Where's that first petal? The first petal is at pi over 6, right? And then there are other petals too. But I'd love to just nail down where that first petal is. And you can just go back and check. If you plug pi over 6 in, you do get 3, don't you? Great. And then if you were just to kind of think through this, if we're in agreement that there are 3 petals, and maybe you're not yet because you've never done one of these before, but if I tell you there are 3 petals, then where would the other ones be pointed if they're evenly spaced? And this is nice and symmetric. Yeah, there actually will be one there. Yeah, so how would you do it? Maybe easier in degrees. If there are 360 degrees in a circle, how often will you get a petal if there are 3 of them evenly spaced? Every 120 degrees, exactly. So, or in radians, it's actually easier. Every 2 pi over 3 radians, right? So that makes sense, because if there are 5 petals, that's actually hard in degrees, maybe. Well, actually not 2 pi, it's 72 degrees, right? But it's just 2 pi over 5 radians. In radians, it's nice, right? If there are like 17 petals, how often do they occur? 2 pi over 17 radians is how often they occur, right? So we'll just do it that way. All right, so 2 pi over 3 units, radians later would be, yeah, over here. You can also just use the picture, right? Why is the board shaking so much? And then 3 pi over 2, I think, if you. All right, so that's the picture. And if you want to just put some petals on there, that's fine. Let's make sure what's going on, though. Let's do. It's 0 at some point. In fact, it's 0 right at 0. Right? If you plug 0 into this, you get 0, don't you? So actually, we're starting at 0. If we're like going to start at 0, then we get r equals 0. And then we're going to sweep up at pi over 6. We'll be out of this petal. At pi over 3, we're at 0 again, as we're sweeping here. At pi over 2, where are we? We're actually, yeah, it'll be sine of 3 pi over 2. And we'll actually be down here at negative 3, right? So it's kind of similar to the last one in that respect. So anyway, I think I'm pretty convinced that this is the order in which it's graphed, and this is the picture. Something like that, right? And again, you can do this on your calculator and verify now that this is in fact the right picture. We got 3 sine of 3 theta. Here we go. Now watch carefully, because something is, we get the same picture, right? But something interesting is happening. I promise, I did 0 to 2 pi. What, did anyone notice that? Here, let's watch it again. What happened? What happened? Yeah, did you see what we see? Did you see that it went around twice? Here it comes. That didn't happen on the previous one. So now we have some insight into why the even odd thing, right? There are actually 6 petals here. It just so happens that when n is odd, the second set of 3 petals land on top of the first 3, right? So I think anyone looking at this, though, would still say this only has 3 petals. But there are kind of 6 petals, right? They just happen to land on top of each other. Yeah. Yeah.
Wait, so on the board, it has n petals if n is even, but 2 n petals if n is odd.
I know, it's because what did I say? 2 n petals if n is even. N petals if n is odd. Yeah, so if it's 3, yeah, that's right. Okay, sorry. I just was thinking I retyped. So if n is 3, how many petals are there? 3.
3.
Yeah. If n is 2, like on the previous example, then how many petals do we have? We actually have 4 petals. Yeah. That makes sense? And if n is neither even or odd, then see what you get. Let's skip those rules here. Yeah, go ahead.
What if n is not natural?
That's what I was just saying. What if n is not what if n is like 1.5? Then you get a really interesting picture. You get some cool flowers, actually. You get, yeah, you should do 1.5. Try it. Mom's gonna like that. For Mother's Day, she might like the 1.5. We're just not gonna study those. We're only gonna study ones that have integer values. But play around with it, right? And see if you can figure out what's going on. That'd make a great IA if you hadn't already done IA. Think about polar curves. All right. So let's actually do some. Let's do some of these, and these are called limaçons, okay? And I'm intentionally I'm on the fly here. I was going to show you the rules first, but I'd rather do what we did before. I'd rather like just show you how to do them and how I think about them, and then, I mean, if you want rules, I mean, whatever, that's fine. Okay. So yeah, the curve we're about to produce, both of these are called limaçons. Right, and you have to say it like real Frenchy, like Mr. Gibran. You have to say limaçon. You have to say, okay, limaçon. Okay, we're going to graph a limaçon now. What is this cool? Maybe choose something bigger than 0 to 2 pi, or what are you doing? Yeah, sure. See some more of it, right? More. All right. So here we go. Let's graph some Frenchy stuff. That's a circumflex under the sea, and that's all I know. Okay, don't ask me anymore. Limaçon means, I think, like snail or something, or huh? I think escargot is like dead snail, and like, you know what I mean? Yeah, exactly. Yes. That's what I'm going to say. I'm sticking to it. You can look it up. I don't know. I'm making stuff up. They don't really look like snails that much, though. Okay, well, will you be the judge? Here we go. Let's plug in 0. And by the way, this is like this is like very similar to the first one, the warm-up. The first one, the warm-up today, part A, was a limaçon. Okay. All right, here we go. If you plug in 0, what do you get for R? It is. If you plug in 0, what do you get? Appreciate your enthusiasm. Okay. If you plug in, when else do you get 3?
You know that's recording, right? So it did.
Yeah. In the pi direction, we also have 3 units here. Okay. And before we go any further, we should also ask the question about this one. What's the range of this function? What is the largest and the smallest R value that comes out of this? It's a little trickier. Yeah, 5 is the biggest R value you could get. Do you see it? And the smallest is no. And it's 1. And the way you analyze these is just like the previous one too, right? You kind of think, you could even think back to first semester, what is the range of the function y equals 3 minus 2 sine x, right? Are you all right? Right? I'm thinking about the up and down sine wave. Ignore. I'm thinking of like an up and down sine wave, right? And its max and min, if we were graphing this first semester, it would have been at 5 and 1, right? Right? You make like your 2 channels, your roadway, right? So, but in polar coordinates, what does that mean? It means the largest value that we ever have is 5. 1, 2, 3, 4, 5. That means that we'll never go out of this circle of radius 5. And the smallest value you just said is 1. That means it will never come inside that circle, right? Right? Because you just told me R will never be 0.5 or something. There'll never be a coordinate on this curve, 0.5 comma something. That's what you're saying. So this entire graph will live inside this annular region. It's like a donut-shaped area, right? Okay. When do you get 5 for theta? What theta value gives you R equals 5? You told me that you would get 5 at some point in your life. 3 pi over 2, right? Because we need this to be pi, right? 3 pi over 2, we get 5. When do we get, what happens to pi over 2? We get 1 there, okay. So the rest you're going to take my word for, but it kind of looks like this. It's kind of a circle that's been squashed down or something like that. Can you convince yourself that it's going to be symmetric around the y-axis? Yeah, it's kind of a, it's called a dimpled limaçon, actually, because it has this little thing. But you can graph it on your calculator and see how good a job we did, okay? All right, what about B? Yeah, she might like that too, like a little heart or something. That's actually not the heart shape that we're looking, you can actually do a little better. Yeah, this is not actually, we're going to do another graph called a cardioid, which is a special case of a limaçon. So I'll mention that too. But you're right, hearts and flowers are both good for a harvester. Okay, so same set of questions on B. What's the largest value R could be and what's the smallest value R could be here? The biggest R could be is 6, yeah. And -2 is the smallest R could be. Do you see it? Yeah. Right? Again, this corresponds exactly to like making those channels on your graph back in whatever unit that was. We were graphing y equals 2 plus cosine 4 cosine x, right? And you'd be like, oh yeah, center equilibrium sinusoidal axis at 2, max at 6, and min at -2, right? That whole discussion is still very germane. All right, so 6 is the maximum. When does it happen? When theta is 0. 1, 2, 3, 4, 5. Well, that's unfortunate. Okay. 6. Okay. Over there. And the minimum value will be -2, you said, when theta is pi. So when we're in this direction, we're actually over here. Okay, that's a little weird. We're going to have to help you through this one a little bit. And then what about in the pi over 2 and in the 3 pi over 2 direction? What do we get? What's R? In both cases, 2, right? So We're doing a great job. Keep up the good work, okay? Is R ever 0? We could even figure out, it's a nice value here. It doesn't always have to be a nice value, but actually is a value you could name in this case. You could solve for 0, right? If R is 0 here, you could solve for theta. It actually doesn't matter to me, okay? But the point is R will be 0, right? But you could figure it out. It's nice, actually. It's when cosine is -1/2, right? So there maybe a couple times that happens. So here we go. You ready? This is the fun part. So something like that. Again, graph it on your calculator and confirm that we're right and that we did it in the right order and everything. Okay. So you can imagine why these are kind of related. If this kind of were to come toward the pole and then go through the pole, you'd get this behavior, right? Huh? It looks like a toilet. It does look a little bit. I'm never going to look at them in the same. Okay. So sad. Okay. This is, in fact, this is the reflection inside of a. If you look down in your coffee cup, and coffee cup has some nice light along the side. If you shine a light in, it'll reflect off the sides of the coffee cup, and you'll get pictures of these things on the top of your coffee. If you ever look. Okay. I'm not saying they look like those. They are limacons and cardioids in particular.
So that's why it's French, right?
Because it's coffee. No, I don't think that was how it was discovered necessarily. There's more to that story, but that's cool. So I'm gonna put these up here briefly. I don't know if I want to like make you write them all down though. These are just like copied directly out of the book. It's just, but it should make sense, right? After doing those two pictures, you should have like more of a better feel than these rules will ever give you, right? But you can read through them and make sure that they make sense, right? If A is greater than B in absolute value, then the curve doesn't come in and meet the pole. But that makes sense because we said, of course, that's true, right? Because the lowest R value we'll ever get is something bigger than 0, right? Or if A is less than B, that's the second case we just did in absolute value, then we do have that inner loop because we get negative R values. That's what an inner loop happens. If R can be negative ever, then that's when we get an inner loop, right? When does it point up or down or left or right? Well, I didn't even think about that. It just happened when I was graphing those. But you could analyze that, right? Sine ones are going to point up and down. You can go back and look at why that happened, right? Cosine ones are going to point left and right. And it's all about that negative sign, plus or minus in the middle here. Anyway, so I'd much prefer just kind of doing it the way we did. So there are the rules. Take a picture. It's in the video tonight. Whatever. Download the PowerPoint. Read the book. That's all. You can watch it. Yeah. I mean, I'll give you a second to stare at it. Make sure it at least makes sense to you, right? Anything there that like sounds weird to you? You're like, oh, I didn't realize that was true after doing those two examples. The only case we didn't do is the first one, right? But I think you can buy that. You'll have an opportunity to do it tonight. Imagine that first case where what was it? I think it was like 3 plus 4 sine theta. Is that what it was? Imagine if it was like 4. No, that's not what it was. Whatever. The first one. What did we do?
It was 30 minus 2 sine theta.
Yeah. What if those A and B values were equal though, right? What would happen? Then our maximum R value would be something, and our minimum R value though would be 0, wouldn't it? So that would just be the same thing, except it would come in and meet the pole. It's called a cardioid when that happens, but so it has another name as well because it kind of looks like a heart or whatever. I do think that that's a helpful analysis, right? Like if you're asking, so like a cardioid, for instance, if you have like if you have R equals 4 plus 4 sine theta or something, that's a limacon, or a special case, it's a cardioid actually. And what is the maximum minimum value of this thing? Well, 8 and what's the smallest value? 0, right? And that corresponds to y equals 4 plus 4 sine x, which you would have done first semester, right? And the first thing I would do in this picture, I would be like, okay, ba, 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 ba. This is going to look like this, right? It's going to be like sitting on the x-axis, isn't it? Right? Yeah.
What was the point of making the have like two more balance?
Oh, why do polar things?
Yeah.
I don't know, because someone needed a card for their mother, probably. And we're like, can you come up with it? These are interesting things, and we need a good way of talking about them. Let's see. Let me think of a better answer. We live on a polar grid, right? Don't we? So if you want to describe motion of things around the Earth, for instance, I think you'll have a much easier time doing it in polar coordinates. Actually, you'll be using something called spherical coordinates, which are slightly different, but whatever. The point is still similar. Yeah.
What does negative polar mean?
Yeah. So let's actually, I'll draw this one real quick. What would that be? So we have 4 when sine is 0. So in these directions, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4, 5, 6, 7, 8, and 0 is the minimum. So this guy looks something like this. Oops, I missed. Oh, that's terrible. Second try. Here we go. I don't know, something like that. So that's what we mean. It comes in and meets the pole, but doesn't actually create an inner loop, right? So, right? And that corresponds to, like in polar coordinates, you might think of polar coordinates as simply rectangular coordinates, where you've taken the x-axis and gone like this into a point, right? You've compacted the entire x-axis into a point, right? Now instead of going like this, it's going, around the middle, right? I don't have much to say about spirals. You did some in your homework last night. Well, that's probably a decent place to stop. The bell's going to ring soon, but I thought at least show you. I don't have anything to say about spirals. It should make sense, though, that r equals theta or r equals theta over 10, for instance, is a spiral. Because think about what happens when you put in r values, right? Excuse me, when you put in theta values. If you put in a theta value like 0, you get 0. But as you put in theta values like, I don't know, 200 radians, you get, for r, values like 200, right? So as theta increases, so does r, and you get this nice spiral, right? So that's why that's happening. It does make it a little hard to graph this, though, but we could do it. I don't know. How about you just plot that one on your calculator? We call it a day.